Hi, I'm Devlin, and my presentation is about a research project in deep reinforcement learning I've been working on this semester. The main idea is that we're trying to leverage the context vectors from transformer modules, which are the current state-of-the-art for sequence prediction tasks, and use them to improve sample efficiency in reinforcement learning. So reinforcement learning as a whole suffers from this bottleneck where even the most impressive breakthroughs, systems such as AlphaZero, Mu0, and DeepU network take upwards of a few 100,000 and sometimes millions of episodes to converge to peak performance. The goal with this project is to use raw image inputs, just like DQN in Atari, but with greater sample efficiency and using lighter networks. How this is done will be with an unsupervised auxiliary task called mass contrastive learning, and this will allow us to learn predictive low-dimensional representations to speed up training. The theoretical structure for reinforcement learning is to frame it as a Markov decision process. So how this goes is that there's an interaction between an agent and an environment, and we want the agent to learn how to perform a certain task based just on trial and error. So the agent starts out in some state, takes an action, receives feedback from the environment in the form of a reward, and then in doing so moves to a new state. This cycle is called a scene in reinforcement learning. A full trajectory of these scenes is called an episode. So we save the scenes to a memory bank known as the experience replay buffer, and after some number of episodes, make gradient updates for training that help the agent optimize for getting more rewards. I have POMDP or POMDP written on the diagram because our experiments are actually, for this project, are for partially observable Markov decision processes, so the states that are seen by the agent don't actually contain perfect information about the environment. So I also need to tell you a bit about both mask training and contrastive learning to give some intuition behind why we're using mask contrastive learning. A lot of this project is inspired by a pretty influential breakthrough in NLP, popularly known as BERT. In this paper, it was found that a self-supervised mask language model was extremely effective for pre-training to get word embeddings. The key innovation here was that bidirectional training gave a stronger context than single directional ones from recurrent neural networks. It's especially useful for transfer learning on all sorts of tasks. Contrastive learning is similar to masked bidirectional training in that it's also a self-supervised algorithm for representation learning. And first I should note that when I say encoder, I'm talking about a map from high dimensional inputs to a lower dimensional representation. And self-supervised here just means that we don't have to provide labels. So like in the case of BERT, you put in an entire sentence, and then it can provide its own labels because it can just mask the words. Anyway, contrastive learning was developed in the computer vision community, and it's been a game changer in that realm since around 2018. And contrastive learning has also been shown to improve data efficiency in image-based reinforcement learning problems too, because it enhances the image encoder. So the most clear high-level description I can give of contrastive learning would be that you want representations of the same image to be close together and representations of different images to be far apart in the representation space made by your encoder. What I mean by same image in this case would be, we'll consider these dog pictures. These are all data augmentations of the same image. One has Gaussian noise, one has the color removed, and the other has a color distortion on it, but they're all clearly from the same picture, so their encoded representation vectors should be similar. Okay, so the overall objective is to optimize not just for reinforcement learning, but for contrastive learning at the same time, based on this loss function in the center of the screen. Lambda is just a hyperparameter, and we've been setting it equal to 1, and that's working pretty well. The Greek letters under Mnih denote parameters of the various neural network architectures that we're using. So for reinforcement learning, the type of setup where we have, we encode the states with a convolutional neural network, f sub theta, and select actions based on any model-free reinforcement learning paradigm that you want to use. This can be DeepU learning, actor critic, or a policy gradient. Through doing all of this, we're adding trajectories to the replay buffer after each episode, and then you update your reinforcement learning loss, or your weights rather. Then the contrastive piece, or the mass contrastive learning piece comes in. It blends the two paradigms that I mentioned before of mass language model and contrastive learning. So take a trajectory from the replay buffer, we mask some of the states with a probability P sub m. We found that 50% works pretty well. So we'll say mask half the states in the trajectory, and then encode them with the same convolutional neural network that you're using for reinforcement learning, and then reconstruct the masked inputs with a transformer encoder by feeding in the whole sequence. And this is just self-attention blocks with linear layers. And then you also have another encoder, F sub theta k. So what you're basically trying to do is you encode the original states, and then you also reconstruct the masked ones, and then you have this contrastive loss, which looks kind of like a log softmax. And basically you want for all of the masked images, you want them to be similar to their corresponding key of the, even though it's a different encoder. And then this is your loss function for backpropagation, and then, typical deep learning training. So I know I'm running short on time. So for ongoing and future experiments, what we're basically doing, this project is still a work in progress, but we're experimenting to see how much the pre-training aids with sample efficiency and also with transfer learning. And currently it's on an environment I coded up from scratch. So it looks kind of like this. It's an agent. The agent is this blue square, and then you can randomly generate the environment such that there's always a successful path, and its goal is to move to the green squares, and it can go in any direction. And if it steps in a red one, the episode ends instantly and it gets a negative reward. And if it gets to the green one, it gets equal weight but a positive reward. But most of the time it's 0. So it's a sparse reward, partially observable and Markov decision process, and it states it sees some distance in each direction. And then if it's off of, as you can see, if it's off of the environment, then it just sees black. And the goal would be to, after we're done with the current experience we're doing, is to see how we can use a transformer to prioritize different trajectories that are on the buffer, so that you don't have to save as many, and then also to use determinantal point processes to diversify the replay buffer and see if that improves training. And the code's not open source yet, but we're hoping to come out at least with a preprint by the end of May, so it'll be open source soon. Thanks for listening.